All right, today we are tearing down the anatomy of a safety system. We're going deep inside API 521, which is basically the rule book engineers use to make sure massive industrial plants fail safely. I mean, think about it for a second. It's a pretty intense question, but it's one that process safety engineers have to answer every single day. You've got these incredible pressures, all these volatile chemicals. The line between everything running smoothly and a full-blown catastrophe is, well, razor thin. So what's holding that line? At the end of the day, it all boils down to one single threat inside all that steel and piping: pressure. If you get too much of it, the equipment that's built to hold it in, well, it won't, and that failure can be catastrophic. So pretty much every safety system we're going to talk about is designed to fight this one relentless enemy. Okay, so let's dive into the core philosophy here. To build a defense that's basically bulletproof, engineers don't try to imagine every possible crazy disaster happening all at once. Nope. Instead, they work from one really powerful guiding principle. And this is it. This is the bedrock rule, coming straight out of the standard. It's called single jeopardy. What it means is, engineers don't have to design for, say, a total power outage happening at the exact same second that a giant pipe ruptures. They assume one unrelated thing goes wrong at a time. It's a really pragmatic way to approach an otherwise impossibly complex problem. So, working from that single jeopardy idea, what kind of one-at-a-time failures do engineers actually have to plan for? Let's walk through a few of the big ones. This one's the classic. You get a fire somewhere in the plant, and it starts heating up a nearby tank. The liquid inside starts to boil, which creates a huge amount of vapor, and boom, the pressure just skyrockets. This is often one of the absolute worst-case scenarios a safety system has to handle. Now, this one sounds so simple, right? A pump is just chugging along, doing its thing. But if someone accidentally closes a valve downstream, that pump just keeps pushing. It has nowhere to go. The pressure just builds and builds and builds, threatening to tear the equipment apart from the inside. And this one is my favorite because it's so subtle. You can have a pipe full of a cool liquid and it gets isolated, valves closed on both ends. Then the sun comes out. That's it. Just the sun heating the pipe is enough to make the liquid expand. And since you can't compress a liquid, that expansion creates an absolutely immense force, more than enough to split a steel pipe wide open. And believe me, we're just scratching the surface here. The actual standard lists dozens and dozens of these potential causes. You've got utility failures, control system glitches, tube ruptures inside heat exchangers. Engineers have to sift through every single credible scenario to find the one single worst case that the entire safety system has to be built for. Okay, so we've identified the threats. Now what's the solution? Let's talk about the last line of defense. The purely mechanical hero that stands between a process and a disaster. The main weapon here is the pressure relief device, and they generally come in two flavors. For most situations, you've got a relief valve. It pops open to let the pressure out, and then it closes back up again. But for super fast events, like an internal explosion, what engineers call a deflagration, a valve's just too slow. For that, you need a rupture disc, which is basically a metal diaphragm designed to burst open in a split second. But here's the really critical part. Picking the right relief valve is almost all about one thing: back pressure. That's the pressure on the outlet side of the valve that's pushing back. A simple conventional valve gets totally thrown off if that back pressure is more than about 10% of its set pressure. So for systems with more back pressure, you have to use what's called a balanced bellows valve. It has a clever metal bellows inside that shields the mechanism from the back pressure, letting it work perfectly even when the back pressure gets up to, say, 50% of its set point. The point is, whether it's a simple conventional valve, a balanced bellows, or even a more complex pilot-operated valve for really high back pressures, the principle is the same. The pressure gets too high, the correct device for the job opens up, and the equipment is saved. It is a beautifully simple, rugged, mechanical solution. No computers, no electricity needed, just pure physics doing its job. Okay, but hold on. We just solved one problem, right? But in doing so, we've created a whole new one. You've just vented a massive amount of potentially flammable, toxic, high-pressure stuff. You can't just let that go into the atmosphere. So now what? Well, the most common, and let's be honest, the most visually dramatic solution is to burn it. You send everything to a flare. And this isn't just about getting rid of it. It's about using controlled combustion to turn something really hazardous into something much, much safer. So it's a three-step process. First, all the relief pipes from across the plant feed into one giant network called the flare header. And right here, this is where that back pressure concept comes slamming back into focus. That huge header pipe creates resistance, it creates back pressure. This is exactly why a simple conventional valve usually won't work here. The back pressure would literally hold it shut. This forces the engineer to choose a balanced bellows or maybe a pilot-operated valve that's specifically designed to overcome that pushback. Okay, next, the whole mix goes into a big vessel called a knockout drum to drop out any liquids. You don't want flaming rain. Finally, the clean gas goes up the stack and is safely burned off at the flare tip. And if you want to understand the sheer amount of energy we're talking about, look at this number, 6.31 kilowatts per square meter. That's the maximum level of thermal radiation, of heat, that's allowed in an area where people might occasionally have to work. To put that in perspective, that is like standing just a few feet away from a roaring bonfire. The flare system is safely handling an incredible amount of destructive energy. So let's pull back for a second and just look at the big picture here. What's the fundamental philosophy that ties all these different pieces together? What's the main takeaway from API 521? Really, it's a defense in layers. First, you have to think like the bad guy. You have to anticipate every single plausible way the system could fail. Then you put your trust in these tough mechanical relief devices as your last-ditch effort. You have to remember that just getting the pressure out isn't enough. Disposing of it safely is just as critical. And finally, you have to realize that things can go wrong anytime, not just during normal operation, but during startups, shutdowns, and maintenance too. And that kind of brings us to one last thought to chew on. This entire philosophy we've talked about is fundamentally mechanical. It's springs and diaphragms and brute force. But today, we live in a world of super sophisticated automated controls, what the standard actually calls high-integrity protection systems, or HIPs. These things can see a problem coming and shut things down before overpressure even happens. So it makes you wonder, in this digital age, is a simple, spring-loaded valve still the best and final defense we have against disaster?